Hello and welcome. This is the programming video for the Doomed demo that I've recently shown on my main channel. Let's have a quick look at that demo, but if you've not seen the video, there's a link in the description. So that footage was taken from the hardware version of the processor, but I've also got a simulator version of the processor, which I actually use for quite a lot of my development when I'm writing code for it now. If you want to get hold of the simulator to have a look at it yourself, I'm distributing it for download on my Discord in the toolchain channel. And with that is the source for this demo as well if you want to have a look at it yourself. It does come with absolutely no warranty. It's about 5,000 lines of assembly language, but it's there to have a look at if you want. Before I really get stuck in, I do want to say that this demo is not like Wolfenstein or Doom. It's got some elements of commonality with them, but there's some things in it which are done differently. So I want to preempt the people who are going to jump in the comments and say, that's not the way Wolfenstein worked. No, this is discussion of the way I made this demo work. I want to start off by having a quick word about perspective correction. Here's a sample image taken from the main videos building my CPU. We all know things get smaller in the distance. So if we were to draw this, but with one side getting smaller, it will look 3D. But actually, this doesn't look quite right. And that's because these two boards are exactly the same width on the screen. They should be rendered with the first one taking up more room. This is the difference between linear and perspective interpolation. To make things look correct in 3D, you want to be interpolating textures with perspective correction. The textbook way of doing this involves a divide for every pixel that we're drawing. However, a divide for pixel would be too much, so we need a shortcut. And whilst I've said the underlying algorithms are different from Wolfenstein and Doom, there are some very fundamental things that the code I've written does have in common with those engines. And that's the way it avoids lots of perspective divides. When we're doing perspective correction, we're dividing by a value related to the depth. And so the way that Doom and Wolfenstein managed to do this quickly is by taking advantage of what we call lines of constant Z. So on these walls, any vertical line contains the same Z value. And so we can just do the divide once for each vertical column. Exactly the same applies in Doom when drawing the walls. And then with the floors, they're drawn horizontally and also take advantage of these lines of constant Z. This is of course why Doom-like engines never had the ability to rotate the camera up and down, although a few versions did kind of fake it, although they were shearing the view frustum in such a way that the lines of constant Z were preserved. Okay, so I've said my engine isn't exactly like Wolf or Doom, so I should probably talk about what it is. It's a 2D portal engine with a one-dimensional rasterizer. And then at the end of the drawing, it's made to appear 3D by drawing appropriately scaled vertical strips. So let's talk about the various steps of programming it. Now the first thing I actually did was the vertical strip drawing. Then I wrote some code and defined some data, defined the initial map. I built the collision for the demo so I could walk around and not walk through walls. Then I wrote the code for horizontal rasterization, i.e. the actual walls themselves. I needed to write some clipping code to actually constrain those walls into the screen. And then I used that to implement the portal rendering so I could make a larger environment efficiently. So what I'm going to do now is go through each of these steps and talk with a little bit more detail about what I did and how I did it. Now the vertical strip rendering code I actually wrote first. Once I had the idea that I'd like to try and make this demo, I put together the code that could draw individual vertical strips, and then I actually tested it to see both what it looked like and how fast I could make it. And that gave me the confidence to go on and develop the rest of this demo with a pretty solid idea of not only how it would perform, but how it would look. So here's a capture from the demo running. Now we've got 80 pixels across, and that equates to 80 vertical strips. So for each strip, we've got 3 sections. We've got the solid fill at the top, we've got the scaled piece of wall texture, and then we've got the ground. What I have is a table in the code with one entry for each vertical column, which defines the scale of that line and its horizontal texture coordinate. So that first chunk of code I wrote takes that table and draws the screen as you see it, and then the rest of the engine is actually building that table in the first place. But the interpretation of this table is the first point in which this actually starts to appear three-dimensional. Making these vertical strips render efficiently was always going to be one of the big performance challenges, so I spent quite a bit of time working out exactly how to do that. Now, my video hardware doesn't have double buffering, so I had to double buffer it in software, but that did give me an advantage that I could change the double buffering code to give me a layout that was more appropriate. So internally, the screen buffer actually looks more like this, with sequential memory addresses being horizontal and starting at the left-hand edge and moving towards the right-hand edge as we progress in memory. Now, this was very useful because it meant that the inner loops that were drawing these strips only had to worry about moving a single pixel through memory as it was rendering. And then the buffering code that flips it into the front screen actually does this kind of transpose and rotate in order to put it on the screen in the correct format. So this is the output from an early piece of test code that I wrote, and I'm going to use it to demonstrate the fact that I actually wrote 3 different routines for drawing these vertical strips, and they handle these 3 sections. So my textures are 16 pixels high. So I have one section of code which deals with drawing the vertical strips under minification. That is where the texture is being drawn on the screen smaller than it would normally appear. The second section deals with magnification, and that's where we're increasing the scale of the texture data as we draw it, but where we need both the top and bottom fill that we're using here for kind of sky and ground or ceiling and ground. And then the third case is magnification with clipping. So if we look at the code here, we can actually see we're scanning through the 80 columns, and for each of those columns we pull in the size and I perform a comparison, and then I can call the individual forms of the vertical strip renderer to see which one is going to be used to render that column. Next up, we should talk about the map and how that's defined. I actually designed the initial form of the map on graph paper. Here's an actual scan off my notebook. And give or take a few tweaks, this actually made it exactly into the demo as you see. Before we move on, I'd like to talk about the line equation. I'll reference this a couple of times in the code and in the description, and if you kind of web search for the line equation, or if you remember it from school, you'll probably find something like this. So this type of equation is defining the y-coordinate from the x-coordinate using 2 coefficients, and it's actually rubbish for our purposes. This is not what we should be using, and it's not what I'm talking about. Equations of this type perform really badly. They can't define a vertical line, and when you start having to worry about mathematical precision, they have very different levels of accuracy depending on the angle of the line. Now, if you're familiar with the kind of maths used in computer graphics, you might instead have been thinking about a line equation that looks like this. With this type of line equation, A and B describe a vector that's normal to the line that we're describing, and if it's a unit vector, this equation will actually give you a signed distance to the line, so it's a lot more useful. But this is not the form that I'm using. This is what I'm using, and I do this at several places in the code. So in this one, A and C are a vector that's normal to the line, but BD is a point on that line. And if that's fairly close to the point you're testing, this preserves a lot more accuracy, even if you've got a fairly lossy numerical representation. So I'm using this because I've got 16-bit values I'm doing the majority of my maths in, and so I need to maintain as much precision as possible. So here's that map, pretty much exactly as it was on the graph paper. I've got a series of vertices and then some walls that connect them. And then the next thing I added was some portals. Now I added these manually with a singular goal of making it possible to divide the map into convex regions by using either the walls or these portals. If I was writing this engine for a production game, I would expect to write some tool code that would do the process of generating these portals and various connected structures fully automatically. But the way I did it for this demo was a fairly manual process just to avoid having to spend a large amount of time building tools for the engine. Now, I've got a couple of things in the demo that need to know which of these regions the world is being viewed from, or where the player is. So the first thing I did was I constructed a very simple, shallow binary space partitioning tree in order to provide that information readily. Now, the moment you talk about BSP trees, people think of Doom, because quite famously, that was one of the first engines that popularized the concept of BSP trees. But Doom had very specific uses for them, and that's not what I'm doing. BSPs are an interesting data structure which have an awful lot of different uses depending on exactly how you construct them and start interpreting the data within them. And this one was just to tell me, for any given point on the map, which of these convex regions it's inside. Each node of the BSP defines a line using the line equation that we discussed before, which hopefully divides the world roughly in two. Here's my first dividing line on the BSP. Now my code is seeking a line that gets as close as it can to dividing the regions in its list in two, but without cutting anything up in a complex way if it can avoid it. So this was actually accidental and not planned that it could find this edge, but I'm quite happy that it did. So the first step in the loop, we would determine which side of this line we're on. Then in the second iteration, we're either testing against this line or this line, depending on which side we're on. Now in the third iteration, it gets interesting because for all of these sections, that third line test, if we were in one of these regions, we've now got our answer. So any point with this color is going to be told it's in this region, but that's because this is a degenerate outside case. If we're in this section, we still don't know which region we are located in. So we have another iteration of the BSP. So this new dividing line means that points in this section of corridor are now resolved, but over here we're resolved for some of it, but not this upper section. And another level of BSP has resolved this tiny little piece of corner here, but it's not really added anything. But then the final level of the BSP has finished off resolving all of these zones. Now those last few felt complex, but we've got a maximum of 6 of these line checks for us to take any point on the map and tell us exactly which of these regions we're in. And that's actually pretty efficient, especially since we only actually have to do that once per frame rendered. Okay, the first use I have for this region data is collision. So for each of the regions, now I can easily determine which one I'm in. I build some basic collision data, and that will include each of these boundaries that I've offset by a fixed distance from the walls. So that means that my collision primitive is actually a point rather than having to implement a collision primitive with any kind of radius to it. And normally you'd put the extra effort in for that in a game, but for this demo I wanted to get there as quick as possible, so I used this shortcut. And I could still use this for a game if all my enemies were the same general size as the player character. Or I could possibly create multiple BSPs for different sizes of enemy. So in each of these regions, I have a list of these edges, and I do have some information about the portals to allow the player to pass through those. The other thing I have attached to each region is a list of the original walls that I might have to render to describe that region. I also have a list of portals, so maybe you can start to see where this is going. But let's talk about how we actually render the walls. First thing to remember is this is a one-dimensional operation. Remember, we've got that 80 entry table that our vertical strip rendering is going to use later on to fill the screen in, but we literally just need to fill in one entry in this table for each vertical column to say what the texture UV is and what the height is. So I always draw that left to right. The height is always linearly interpolated. As is common in 3D graphics, we're using a planar perspective projection, which has the useful attribute that straight lines are always preserved, so we can get away with doing linear interpolation here. I use a 16-bit format. However, I've got two versions for interpolating the texture U coordinate. I've got a perspective correct one, which interpolates with 24 bits precision, and I've got a linear one that interpolates with 16 bits precision. Now we talked about how we need the perspective correction to make it render correctly, but some edges, if they are particularly short or fairly parallel to the screen or far away, it doesn't really matter very much. So just to help with the speed a little bit, I've created these two versions of them, and one will operate a bit quicker. Here's an example from inside the game engine. Let's have a quick look at the data that I'm actually interpreting in the engine. So for each of those convex regions, I've got a collision table and a render table. So once I've used the BSP, I can go and pull one of these two chunks of data out. Here's an example of the collision data, which is basically just showing me a series of the line equations that we discussed. Now on the render data, first thing I've got is the vertex count, and that will tell me all of the vertices that are referenced within that region. Now there are some possible additional optimizations I can do because we know that these mostly operate in a loop because these regions are convex, but I just go through when I'm rendering a region and I will transform all of these vertices. So when I have an edge list, I actually calculate and store the address of the transformed version of this vertex rather than simply specifying the vertex index in this data, because that just saves me some time when I'm actually processing the edge list. Additionally, I have the texture U coordinate for each end, and I also have a byte that specifies the material. And this is actually just an offset inside the texture. We'll talk about the portal data in a moment. Now I said at the start this is a portal renderer, so I need to explain what that is and how it works. So we start with a view origin, a direction and a field of view. I'm using a 90-degree field of view. Initially it was because the maths were really simple, but it just kind of looks right. This camera position and orientation is roughly synonymous with this scene we've got here. So in our first step, we have to identify what region we're in. So I take this camera position, recurse into the region BSP, and that will tell me that this leftmost region is where the camera is located. Now, when we looked at the code just then, we can see we've got some collision data, which when I update the player's movement, I'll just use to make sure I've not gone through a wall. But from a rendering perspective, it will give me a list of vertices, which I'll transform, and then a list of edges, which I'll go through and render. And working through this edge loop, I'll find that only one of those passes my initial tests. What I'll do is I'll clip that into this view volume, and then render it into the vertical strip table. Now we've actually now filled in a notable chunk of that table, which will be turned into a decent chunk of the rendered scene, but we do have the whole section here that we haven't worked out yet. Now in that same region list, alongside the walls, is a list of portals. Now these are very similar to walls, apart from instead of render material data, they have a link to the next region they're in. So we take the code that we used to render this region and we look at this region as the next one. The boundaries of the view volume we created from the left and right side of the screen, but now we replace that with the left and right extent of our portal once it's clipped into the original view area. So now we do exactly the same. We transform all of these vertices, and then we look at our entire edge list, clipping it into our view area and rasterizing the appropriate walls as required. Of course, we've still got a portal in the list here that would be rendered if it was a wall, so we're going to rinse and repeat. We're now interested in this region, so we take the vertices of that portal and turn that into a new view volume, and now we're rendering this region with a yet more constrained view area. And in this case, only this back wall is actually going to result in a piece of surface that is rendered, and we've completed the rendering of the scene. Now, this source file, portal.inc, controls the code that actually performs the generation of those view volumes. And I've got this value at the top, which is a constant value which defines the maximum number of recursion steps it will use for rendering regions. Now I've got that set to 3, which will get us the scene we just looked at. But if a nav portal were visible, the code with that set to 3 would stop and not draw the next region. We've actually covered most of the high-level sections of code now. One thing we haven't talked about is clipping, which is necessary because we need to clip either walls or portals into the current view volume. And mathematically clipping is easy, but it does need precise mathematics. So imagine we've got a wall or a portal and we're going to clip it by this line, which is a boundary of the current view volume. First thing we're going to do is evaluate the points at either end of that line by the line equation, and that will give us the distance in front and the distance behind. Now we can calculate an interpolation value with this formula, Essentially, we're saying we divide the distance in front by the total distance of the line or wall. Any attributes of our line we can then interpolate using that calculated value. So if we do that to the x and y coordinate, we would get the point at the intersection. If we did it to the u coordinate, we would get the u coordinate here. Now, one thing it's worth thinking about is on my processor, divides are expensive. I've got a whole video about writing a very optimized divide routine, which only has 7 bits precision in the numerator. And that one's quick. So if we can use that for as much as possible, we can keep this thing running smoothly. Unfortunately, 7 bits is not enough here. If this red line represented a long corridor, then with a numerator that's only 7 bits, that would mean our clipping would have an effective resolution of 1/128th of this line. So imagine walking down that corridor with that poor resolution. The wall on the left or right, whichever it is going to be jumping around badly. So we need to be able to clip it at much higher precision. Now I could use a higher precision divide, which I do have, but it's slower. But then we'd need to use larger multipliers as well. And we start doing quite a lot of operations to get there. But there was a better way to handle it in this specific circumstance, and that was to use successive approximation. Now, I wouldn't normally consider using this for this type of problem, but it turns out in the very specific case of an 8-bit processor where larger divide operations and larger multiply operations become substantially more time consuming, this becomes a very good way of controlling the precision of the operations you're doing. So with this algorithm, what we do is we calculate the center point of the line and all of the attributes we're going to be interpolating. And that will include the distance. So then we can look at the sine of the resulting distance and decide whether or not we are, in the next iteration of the loop, going to be looking between the point at the front of the line or the point at the back of the line. So then we repeat again. This time we've gone to the back, and now our 2 points are this one, and we're going to bisect this again. And you can see how we rinse and repeat, and each step we narrow in on the intersection point we want. Now for us, this process actually has some interesting properties. Firstly, we don't have to make a very granular decision between 8-bit maths, 16-bit maths or 24-bit maths. The number of times we run this loop we can control with a lot of precision. So doing this with 7 iterations of the loop will get us a similar level of precision as using our fast divide operation, but we can go to 8, 9 or 10 iterations of the loop and get a lot more precision without having to make the jump to a 16-bit divide. It has another property which is useful to us, and that's the granularity is very contained. So if we stopped at this point here, it may not be a perfect intersection, but we should have our values interpolated to this exact point. So if we're walking down that corridor, we shouldn't have a wall that's jumping around because we've got a lack of precision in the interpolation. We might just be seeing a small gap in that wall. Now the clipping source file here actually contains a bit more logic there. What I do is I calculate the distances to both sides of the view volume for both ends of the wall, and then I take those sines to construct a 4-bit number and index into this table. And this is a really clean way of computing the different operations that I expect to have to do on the resulting wall segment. And I have a similar table for the portals. And then you can see this fairly simple implementation of the successive approximation, where I create the interpolation between the 2 points, which is very straightforward because we're using 50% exactly. So we can do all of that with shifts. And then I do a sine bit test on the resulting distance value and then work out which of the 2 vertices to replace with the interpolated one. Okay, I think I'll finish off with just a few closing thoughts. It's worth looking at the performance of the overall demo. The drawing of the vertical strips and then the copy to the main frame buffer takes roughly half the time. And that was as expected, so I spent a disproportionate amount of time optimizing that. The other half is the horizontal rasterization and the transform code and the movement logic. My transformation and perspective projection code for the vertices definitely has some room for optimization. I actually end up doing the perspective projection for many of the vertices twice because they exist on both the start of one wall and the end of another. There would be gains to be had storing it in such a way that that information could be retrieved and only done once for each of the vertices, but it would have been a layer of logic that wasn't necessary to get it up and running. Adding enemies to this wouldn't be too tough. You would need to add a dynamic list of additional render objects into each of those regions, and then when you were recursing through portals, you would render the room and then render the objects within them with the appropriate clipping to the same view volume as you were observing the room through. Now, doors would actually be a big help to this if you were turning it into a game. Not only would it help you control the gameplay and be an interesting addition, but you could also use it to prevent recursion of the rendering between regions when the door was closed. That would allow you to create much larger, more complex levels without ever worrying about needing to recurse too far through the list of regions. Obviously, my resolution on the VGA is very low. As I develop this further, I would like to see if there's anything I can do to increase it. Now, when I have the tile data in addition to the tile map, I might be able to construct some specific tiles which would allow me to fake a higher resolution. Be interesting to experiment with. And lastly, before I go, I'd like to thank my generous patrons. I really do appreciate the support. Okay, well, I hope you found it interesting. I've only been able to go into a certain amount of depth on some of the core areas here, but I'm hoping I've given a reasonably good broad overview of the way this demo works. Hope you found it interesting. Thanks a lot for watching, and I'll see you again soon. Goodbye.